Long and this杨彩珍 and this 郑永杰 and this solution
And opponent.
I'm the captain of the languages team, and this is Jeremy, this is Wayne, this is Tony, and this is James. Thank you.
And observer.
Hi, I'm the captain of MD Joker. 谢婉瑜、林晨杰、庄玉珍、黄依恩、许哲瑞。
Well, in this part, we don't need to challenge your question. Each team already choose their question. So now let's start the fight, and reviewer, you have 5 minutes to prepare. If you are ready, just let me know. You can start immediately. Oh, yes. And please write the representative. OK。再秀一下看一下，第三层那个。
他们现在是可以用的，
可以马上用。
对。
那好，紫色就是。
会不会可以切切看？
Okay, however, I'm Tim from Houston, and today I will report the dancing statement. And this formal statement will explain the phenomenon and investigate the phenomenon affects the sticky motion. And we focus on the fix the button and use hand to turn the top and observe this phenomenon. And this is what the experiment. And this is the thinking I use. The quantity is 174 grid. And the diameter is 6 and 0.45 centimeter. And the turn is 85. And the height is 5.5 centimeter. And the station is this. The station is 2 meter square. And then it's where I use the soft form foot and fix the button in the table and use my hand to turn the knob and release and use camera control. And it's a follow demonstration. After we release the sticky, I can observe this phenomenon. I observe two phenomena. The one phenomenon I call it momentum from the A. We can see the sinking vibration regularly, and it's the turn. Is when we turn the top from this and A, and this momentum from B. We can see that after the short regularly vibration, it will become like this, and it's our theory. My theory is to press the button and use hand to rotate it to turn the top. The energy will be saved and become a constant electricity potential energy and actual electricity potential energy. And this shell shape is a very important diameter and its premium. And J is the ability of the spring to succession and then and is to release the personal information. And R is very simple, is the distance from the force verification point to the rotating action. And the contour and rotating and just about a fixed action. And there are three vibrations we can observe three direction vibration, and this one is a personal vibration. Yeah, if you see the sinking against that, you can see the rotation like this, and this is the head person. It's the energy wave. It's one of the potential energy. The energy wave is set like this. And the Q vibration is the actual vibration. And we can see the height of the sinking will be changed during the vibration. And this is the energy wave set like this. And the n is not equal to the spring mass. This is the 5.8. Energy is the very we can see the sinking right side. We can see the sinking vibration left and right. And it's equal to the mass turns to not equal to the spring mass. This is the mass like this. And this is our Okay, this is our focus point. The focus point 1 is the momentum from the A, and we call it normal. And the focus point 2 is the momentum from the B, we call it complex. And we will investigate the vibration frequency of the two momentum fronts. And we use checker to check the side of this sinking after we release. And in this condition, we turn the top of the sinking 7 times. As the next momentum, we turn the top of the sinking 8 times. And this is analyze. And close to rotating the top 3 times clockwise, we can see this. And after we use checker to check this point, I use this data to do the STFT. And the data has the 2 directions, the X and X is Y. And this X direction, we can observe the vibration frequency visually, and there the vibration. The vibration frequency like this, and length of vibration time of this 12 seconds. And this is the Y frequency. This is the Y duration frequency. We can see the different from the X, the duration more accurately and equal to the duration X, the vibration time is less than 12 seconds. As needed, there's the next rotating next momentum point is B. And we rotating this spin 8 times clockwise. And also checking, use checker to check this point and use it to analyze. We also use it to do the STFT. They look very like the next, the 7 clockwise rotating, but this is a very big difference. Equal X duration, the vibration time is distant 4 seconds. But I'm rotating rotating it 8 clockwise is more than 7 clockwise. And next is the Y direction. And the Y direction use the STFT. We also can see the vibration are more regular than X. Yes. X. And I come back to this chart, this photo. I will explain why the sinking has a 3 direction vibration. And I think this is the streets are now average, but I can use I to observe the streets. So I use console to do the simulation. And this chart we can observe when we turn the top of the sinking, when we release and it starts with dancing, we can see the streets in the sinking are not average. And we use it to weighting the chart, and we can see the move like this. And there also has the 2 frequency. The frequency X and frequency Y has meet the tube division. We see the vibration frequency are very low, and at a low vibration frequency, it has a height and perpetuity. And this is our conclusion. Our conclusion is the amount of the force when we apply force affects the spring motion fundament, and the curving value of the switching to sport mode in the 7 labs. Okay, this is my report.
So, Foreman.
Okay, so my first question is, can you go to the page 15?
Yes.
Okay, so what is this? What is this? M axial equals 1/3 of M. What is this?
It's the mass in this the spring mass is not this, right? And it's the mass applying the moment.
So you, oh, okay. So you have to calculate the kinetic energy.
Yes, yes.
And please go to page 24. What is STFT?
After I use checker to check the point, and I use STFT to analyze the frequency.
So the yellow areas in these two means that it has these two dominant frequencies, right?
Then I think also that is equal to
How do you measure the 1/2 I omega squared? In the theory, next one. Yeah, so how do you calculate the rotational energy?
the rotational energy.
Hands up. opponent. That's the opponent.
Okay, so I'm the opponent of the Lagrange's team, and I'm going to report on problem number 5. Opposed problem number 5. Yeah. Opposed problem number 5. So this is the problem recap. And I think the major mixed points are they didn't have enough discussions and the quantitative influence. The problem statement explicitly mentioned that the affected parameters and explanation, and they should have done more parameters and incorporate more theory into their experiments. Okay, so the general pros and cons. The pros, well, first I must congratulate you guys that you have a well-organized report and you have clear videos. However, you lack intuitive explanations of why there is a wave forming on the sides. And you also lack quantitative analysis, for example, the frequency of the waves and how they are formed and the calculations of their theory. Also, you did not have comparison with the experiment and the simulation. You also have bad time control, unclear definitions of the symbols, and difficulty with aligning with the problem statement. The labels are also unclear. First, the report overview. Well, in the preliminary experiments, they defined their parameters and they discussed the two motions, which is the stationary and the jumping motion we saw in the experimental video. Their setup is not robust, and they do not have a launching mechanism, meaning that you guys use your hand, and that might also affect its motion. And in their modeling process, they model the torsional potential energy and axial elastic energy, and they also drew a force diagram of their theory. However, they did consider vibration, but they did not consider dampings, but even though it's a dissipated system. And finally, in their experiments and analysis, they discerned their movement has two patterns, which is pattern A and pattern B. The first one being normal, and the second one being more complex. And they also use console to simulate their behavior. However, they do not have quantitative explanations of their phenomena. Their Fourier peaks are also not calculated, and their actual slinky parameters differ from the simulation. It should have compared more, like it should have to be similar. And the labels of graphs are also unclear. So may I proceed to the discussion? Okay. These are the discussing points that I will discuss in the next 10 minutes. And first, it's a modeling. They did consider force and motion, but they did not consider damping, which is a critical part of the phenomenon. Their experiments and setup use hand, and I think I will discuss with them how to set up a contraption that will allow a more precise release of the slinky. They also need some clarifications on frame rate and how they film their experimental videos, and data analysis on how the Fourier graph can be analyzed, and they did not explain their two major frequencies in their graph. So, before we take the photo. So, the first point I want to raise is that, may I take a look at your experimental videos?
Please.
It's okay, anyone else that is. So why did you use your hand instead of a release mechanism? So we can more clearly define the releasing conditions. Why did you use your hand? Okay.
This is a table and it's a group. Actually, I need now how many times I actually. So this is a mark.
Yes, I know. You can just count how many turns you have, but I mean that it's a releasing count. If your hand doesn't release, if both of your fingers
no, this is the first problem, and actually
I know how you turn, but I'm asking you if there's a possibility that one of your fingers exits before the other one, and thereby affecting the motion of the slinky.
yes, I think they will affect the result, but I think the result repeat.
Well, I think it still might matter, because if one of your hand releases early, then the slinky might also have a rotation, and that might affect its motion. And this
Yes, so it have a sweet duration vibration. It's the point of the company. They made a sweet duration
Judges, may I have a?
I think they will address the
Okay, so might I suggest that you use release mechanism in your future experiments? Yeah. So, for example, this is a sensing and perhaps you should use a clamp like here, and then maybe a motor to control the clamp so that it can release. Then we can get more precise experimental results and analysis. That's the first point. And the second point I want to raise is that can you go to the console simulation page? And you can play the. So the first point I want to raise is that this is not a sling.
Yes, this is D101 PF5, right?
Yeah.
And I use console as one purpose. I want to prove. I say the street is not average in the speech we have released.
You mean that it separates?
The street is not average in the speech.
Also,
And
so you
I
don't
want to
use
prove
it.
it because I can use I to observe it.
Then did you compare this to your experimental results or analysis of the stress?
Yeah.
Yeah, I know it's not average, but can you have a kind of parameter that is explaining this, or a theory that can also explain this?
No, I use experiment, but I can, if you use this to experiment, I can observe the street is not average. Because the street average is, it can use eyes to observe.
Okay, so you're only using this to say that it is not average.
Yeah.
And in addition, in the experimental video, even in the jumping stage, we also see that it jumps. It jumps and it also has rotation. But in this simulation, we didn't see that it has any rotation. So this is truly an accurate model of your prediction.
Actually, it has a rotation. You can see the simulation time is 2 seconds, and rotation is very small.
Yeah, it's very
It's
small.
the rotation.
In the experimental video you showed earlier, the rotation is quite large, right?
Yes.
And so this doesn't really fit with your phenomenon. So I suggest you maybe consider the equations for your governing motions of this thing, of this spring, and maybe you can rewrite this so it fits the slinky phenomenon. Okay, my next one I want to raise is.
I can.
Okay.
Actually, this is rotation. But if you use this, and not all characterize one, just the small. And really, that is the like this. There was a vibration like this.
Oh, so you mean that for only a few terms, maybe one term, a few terms has a phenomenon similar to this?
Yes.
But if you only release only a few terms, will it still separate and become this closer to the spring configuration? Won't it just stay completely still like this? So say when you twist one turn, right?
Yes.
Then it's okay. Don't figure out. Then it's completely still.
Yes.
It doesn't jump in the experiment, right? In the experiment, right? So it's still a linear model.
You have jump like this.
Yeah, I know, but the coils don't separate. And I think that's the main problem. Now, can I take a look at your STFT analysis?
Which kind? 7 or 8?
The first one,
This one.
24. Yeah.
Yes.
Okay, so how can you explain that there are two peaks? There's one near the 10 hertz and there's one near the 4 hertz. Not hertz, 10 seconds and 4 seconds.
This two, there is ambiguous vibration. That's
Vibration. Yeah,
There's a more ambiguous.
And you said there is a vibration and that's talking about the peaks, right?
First I use checker to get the data, right?
Yeah.
And use data to do activity. And in twist time, we can, in the video, in the twist time, have a more ambiguous vibration console is because the street is not average.
Can you say that again?
The street is not average when the city is dense.
The stress is not average.
Yes.
Well, I think I can provide another explanation. So going back to your experimental videos, is there a total entire duration? So in this experimental video, we see that as you release, there's a wave on the side, right?
Yes.
But right now in this stage, it doesn't have any wave, correct? And then another wave starts. I mean that anyways later. Okay, so there's a wave, right?
Yes.
We observe a wave. And when it travels to the bottom, it kind of disappears or bounces back.
Yes.
And then the wave starts appearing again. Right? The wave starts appearing again.
Yeah.
And in your theory to explain this, well, I don't think, but anyway, back to the SDFT analysis, I think that there is two governing
Yes.
frequencies in this phenomenon. One is the tiny vibration.
And then maybe recording the case. Okay.
So there is a tiny vibration.
Yeah, there's two previous vibration techniques.
Yeah.
And in something that never stop.
Yeah.
Not stop.
Yeah, I kind of
Yeah.
stop and then
So you
resume
see,
again, right?
you see this chart is the activation. Activation is this test.
Okay, I know, but we still see that it kind of goes stationary. And I think there are two kind of periods. One kind of period is the tiny frequency period, and the other is the large kind of period, which is the between the stationary period. And I think that's covered in the SDFT analysis. Okay. Yeah, and maybe the time period also matters. Maybe you need to do more research on this. Yeah, and what is your frame rate for reporting this phenomenon?
What's the
Frame rate. So okay, let's just move on to the next question. And how do you measure the rotational inertia? The one half I omega squared. Yeah. Well, how do you measure that?
accurate?
Because I don't think a lot of theory is kind of connecting to the experiment. Yeah, and does this really does this like describe the motion of the mass you track on the side?
Yes.
How?
You say I.
I mean, what is the predicting power of this theory?
Also, for example, the theory itself like this.
Yeah, but you said like the conservation of energy, correct?
Yes.
But you didn't do any like energy over time diagram. Like for
I
example,
think they can be observed like in the
yeah,
actual release.
yeah, we can see it. There's energy, right? But
Yes.
you didn't really quantify it. So if we want to prove that there is a conservation of energy or something like related to the energy, you should like plot energy versus time or something, and we can see how it changes.
I don't know how to measure.
Oh, you don't know? But you measure it in the.
Energy to
Let me just show you. So, for example.
Time's up. Apollo, you have 1 minute to summarize your conclusion.
Wait, hold on a second. So we talked about the console simulation and how it relates to the second kind of motion, but I don't think it really predicts that. And also it lacks a lot of more experiments because the Collins statement explicitly states that it needs to explore the possible parameters that is affecting its motion, and this theory does not have a lot of predicting powers, despite they claim that they can measure the energy. And he also didn't show this in their results. So I think there are lots of flaws in the experiment, and maybe they can do more exploration of the theory and how it kind of predicts the motion of the mass over time. Okay, thank you.
Now, review, you can take the floor.
So the first one, so in this experiment, which parameters we consider influence
the harmonic test I took. And the value of the is only one is and how many times the sleeping.
You mean that what are the parameters things like that, and how it affects the waveform motion.
Okay, so among the parameters, what do you think will be the most influencing factor that causes the dancing of the signal?
You see the plan.
I mean, the most influencing factor that you have said.
I think it's how to turn the speed.
Yeah, I agree. So if you make more turns, there will be more deformation, and the forces will be different, and maybe that will change how the acceleration and velocity change over time.
So next I'll ask about CO for the important factor. Do you think your CO is suitable for your experiment?
I think this. Oh yes, I think yes.
For the opponent?
I don't really think so, because, for example, if you finally have managed to maybe measure the kinetic energy, then 1/2 mv squared, right? But we know that v is the velocity, but we don't know its direction, so we can't really predict that which direction the mass will go. So I think a better theory would maybe to analyze the forces at play here and how it affect the the force side.
Then for the opponent, to have a better view of this experiment, do you think how many cameras do you think you need to have to record this motion?
Actually, I think we can just use one to capture the whole phenomenon. So, for example, if we have a camera right here, and it's facing here, right, and there's a sinking. If we build a mirror over here like this in a 45-degree angle, then we can both capture the side views of the sinking and also how the top view changes over time. So one is, but we need 2 or 3 to capture the 3D motion.
Time's up. Or you can start your presentation.
Honorable judges and fellow competitors, I'm the reviewer from Team Management. I'm going to review problem numbers and dancing sinking. So I think this is the problem statement, although there's no main focus for the report. So first is the overview for the reporter's presentation. So for observation and survey, as we can see, he has 2 movements, the normal one and the complex one. Then he has the torsional elastic potential energy, and also from the axial vibration and torsional vibration. And for experimental method, he tested the parameters of, he tested the numbers for this. So for data analysis, he has tracker to track the side of the slinky, and also he has simulation. And for conclusion, he has that the amount of force applied affect the spring's motions pattern. And secondly, the critical value of switching moment, the movement is 7 times. And pros and cons for the report are including pros of clear experimental steps. And he also explains some relation between their equation and experiment results. And also, for cons, he lack of organized analysis of the data, and also clear explanation for the phenomena, and his graph lacking theoretical field. And pros and cons for the opponent, he has well-organized remarks, though they fail to have an organized viewpoint. And so for the discussion, the first question is about using hand to start the slinky, but maybe some mechanism should be considered. And then also jump and rotation isn't demonstrated in the simulation. And then he also asked about the purpose for the simulation. So the simulation doesn't fit the experiment that he has done. And he also asked about the 2Ds that were shown in his graph. So as for me, I asked about the parameter in this experiment, and they both answered the time square of the thinking. I also agree about this. Then it's the suitability for the theory, and I think that his theory maybe, as for opponent said, I think his theory isn't the same as what he has done in his experiment. This is for my opinion.
Reviewer, the reviewer, you can take the floor.
Okay, this is my first, I want to say. So, I use console to do it. I only want to know one time. One thing is the strain is now average in the steam queries, and I use the main time I categorize the steam to know how much energy I input to this steam. So I only categorize 7 times and 8 times, and I think next time I can use the machine to release the stinky more perfect, because before I use the hand to release the stinky, so I can ask the sweep division by version. If I use the very perfect structure to do this figure, maybe I just can ask the 2 division, and I can still parameter of the effects of the rotating of the slinky is how many rounds I turn. I think in my experiment, I think this it's only this. I think in my experiment the main condition for everything.
So now is the question time for Julie.
How come the elastic properties last matches did not show up in any of your formula?
Because I use the sense thinking, so I think this is the mistake.
But you cannot be sure with only one sleeve.
Is that only this?
Because if you want to check its dependence, you need to have at least two. Isn't that right? That the phenomenon observed is related to a certain elastic property, then you have to have two samples at least.
Yes.
But you use the same sleep the whole time. I think the proponent may answer my question.
Oh, okay, so I think there is also plastic slinkies, and maybe you can use that to change the material and and that would also change the elastic one.
About the
I think we can use different materials obviously and compare them.
Sure. If you want to ask question.
Oh, yes, it's because use the different materials, so I need this experiment. But this experiment will affect the result, but I only use the one sleeping, so
That's one point, but the other point is, how can the theory in your description no modulus of elasticity appear? You only have effective mass, you know. So you got it.
You use how many terms to count the energy storage, right?
yes.
So how about the energy storage in actual physical quantity? What is the physical quantity of the storage energy?
Just the
Yeah, the physical quantities of the storage energy, what's that? The unit of the energy.
I don't actually
There's that?
Okay, so I think if we really need to get like an accurate representation of the energy, then of course I would look into the potential energy and of the elastic energy, right? So
No, I just want to know what's the unit of the
Oh, the
storage
unit?
energy, yes.
then is it just joules?
I don't know.
Oh, so
Okay, so you will use joule as the unit and measure the energy instead of the terms, how many terms. Okay.
Do we have further questions? So now it's the scoring time.
Hello, I'm to ask questions.
Okay.
I started it.
Okay,
Yeah,
sure, no problem.
But
We still have
we
time.
can take advantage of our time.
Yeah.
You just interrupt me, so I have to think about what I'm doing. Now, what's the difference between stage and a spring, regular spring?
Oh, the distance from the distance between the
He couldn't be compressed. Simply
It can be stretched, but when you compress, there's no resistance. So,
yeah, and I also agree to the slinky can compress, and I think there are also properties of the slinky, like such as maybe the spring constant might change.
but when it's stretched, it behaves more or less like a spring.
Yeah, and so we can observe like the weight of each of the coils more clearly. So the coils will be all concentrated at the bottom, while the regular spring would just like be more evenly spaced.
Of course, even that reason.
We can start.
Yeah.
Ready? Now the score for the reporter, 7 4655. Score for opponent 7768. And score for reviewer 75567.